So the story that we want to think about today is the idea of motion with constant acceleration. And we're still thinking about things that are moving just along a straight line. So just you're thinking of an object that maybe starts at this point and then moves along a straight line to another point. So this is, we call this the starting point, or typically it's called the initial point in the segment. And then this is called the final point. And the key thing here is that we have motion with constant acceleration. So the acceleration during this motion from the initial position to the final position is constant. Now that means that the velocity could change in principle. Unless the acceleration is constant at 0, then if the acceleration is constant at any number, that means that the instantaneous velocity of the object at the beginning is different from the instantaneous velocity of the object at the end. So that's called the initial and the final velocities. And the other pieces that we've learned about so far when we're describing motion is something called the displacement. And the displacement always points from the initial to the final position. So this is called the displacement. And since it's just along one direction, let's call that direction X. And then that becomes our displacement. And all of these things, you notice that I'm putting these arrows on top of them. And these arrows just mean that the direction is important. So it's important when I'm describing the displacement that it's in this direction and not this direction, for example. And we indicate this with positive and negative signs in some coordinate system. Now, I drew these things on sort of a bit of an angle on purpose, just to let you know that it's really not important for it to be exactly horizontal and exactly vertical. As long as the motion is along some straight line, then all of the stuff that we're going to say today applies. But for simplicity, sometimes we just draw it horizontally and we call that the direction X. And here are these 4 variables, and the additional variable that we want to care about is something called the time interval of the segment. So for this segment of motion, sometimes called uniformly accelerated motion, or motion with constant acceleration. So uniformly accelerated motion means motion with So this UAM stands for uniformly accelerated motion. And for this segment, there are 5 what we call kinematic variables that we care about. And they're all indicated there on the diagram, these 5 kinematic variables. The initial and the final velocities, these are 2 variables that we're going to think about separately. So the initial instantaneous velocity and the final instantaneous velocity. Oh, I misspelled it when I spelled it instantaneous. So I missed a whole bit of it. So these are the initial and the final instantaneous velocities, v sub 0 and v sub f. And then we think about the displacement. The position, position initial and position final are important, yes, but their importance is really so that they tell me what the displacement is. So if you want to always break it down into initial and final position, that's fine. But I typically think about it as a displacement, and that's the difference between the final position and the initial position, as we've seen before. And then we think about the acceleration during the segment, and that's constant always for us. So that means, as we'll see later, that if I find the segment in which the acceleration is changing, I need to break it into multiple segments in which the acceleration is constant in each. So it always has to be constant for us. And as you've seen, we use the letter A to think about the constant acceleration. And then there's something called the time interval. And we just use the letter T to think about that. But it really means the time difference between when I started and when I ended. So these are called the kinematic variables. And it's really important in this section that you always identify the kinematic variables for the particular segment that you're thinking about. And these kinematic variables are related to each other by a set of equations that are really derived from the definitions that we've had so far. So the definition of the average velocity, if you remember, which is the displacement divided by the time interval, the definition of the acceleration, which is the change in velocity divided by the change in time, and so on. So if I take all of these and I wrap them together, and I find the set of equations that relate all of these five variables together, we find a set of kinematic equations. There are four of them. They have a slightly different form in the book than what I'm going to use here, but you can easily see the relationship between the kinematic equations as they're stated in the book and as I'm going to use them here. They have no particular order, but you can think about them. There are four of them that are important to remember. And the first one says that for constant acceleration motion, and by the way, these are only valid for that. If the acceleration is changing, then I have to think about it differently. But for constant acceleration segment of motion, there's something called the average velocity, and it's defined as half the initial velocity plus the final velocity. Right. Sometimes we drop this F here because if you just label one of them as the initial, then the other one becomes the final, right? But you can keep it there to remind yourself. It's up to you. So this is the definition of the average velocity for a constant acceleration period. In general, if you remember, the average velocity is defined as the displacement divided by the time. But if you work it out for a constant acceleration period, this is what it gives you. Now, as you think about the displacement in this case, the displacement is going to be equal to that average velocity multiplied by time. So this is one equation here. This is a kinematic equation in which you say that the displacement is equal to the average velocity multiplied by the time interval. Right? And then there's another one that relates the displacement to the initial velocity, the time, and the acceleration. And there's one that relates the final velocity to the initial velocity, just from the definition of the acceleration, because the acceleration is the change in velocity divided by the time. So if you were rearrange that equation, this is what you get. And then there's finally one in which if you plug this first one here into this one, what you get is an equation that looks like this. So these really are our four, sorry, this one was a definition equation. So these really are our four kinematic equations that we're going to be using to solve any problem in which there is uniform acceleration motion. As you can see, in each one of these equations, the four of these five variables make an appearance. So here I have five variables, five kinematic variables. I have four equations. In each one of the equations, you'll find four of these variables. So the first one, for example, you find the displacement, initial and final velocities, and the time. The second one, you find displacement, initial velocity, time, and acceleration. The third one, you find final initial velocities, acceleration, and time. And the last one, you find final initial velocities, acceleration, and displacement. So that means that each one of these equations has four of these variables in it, and it's missing one. And that sometimes is useful to note. It's useful to note which one is missing from the equation, because that makes it easier sometimes when you're trying to solve problems to identify which equation is going to be useful to you. So for example, the first one has the displacement of both velocities and the time, so it's only missing the acceleration. This one has the displacement, initial velocity, time, and acceleration, so that means it's missing the final velocity. This one has initial and final velocity, acceleration, and time, so it's missing the displacement. This one has both velocities, acceleration, and displacement, so that means it's missing the time variable. And this is only something for you to note because it sometimes helps you identify which equation is going to be useful when you're solving a problem. But in general, this is really what you need to know, these kinematic equations, and they're a function of these five variables. Now, to finish the story here, because really the story is almost done, which is that suppose you have a motion in which you have something like, let's say, a simple problem here. Maybe we can solve the whole problem in a second. But suppose I have a car like this, and then this car travels, starts at some velocity, and then it travels, accelerates some acceleration, reaches another stage in which now it's moving at another velocity, and then maybe it brakes. Now it hits the brakes, so acceleration now is different than this acceleration, and then it ends up at the end, and so on. Now, what I'm trying to show you with this kind of example, which we're going to solve something exactly like that, is that sometimes during the motion you get two different accelerations. In that case, what you have to do is you have to divide this into segments. You say this segment I can treat as one segment that has these 5 variables and these 4 equations, and I can solve just one segment. And then I treat this segment as a new segment that has new 5 variables, and I can apply these 4 equations again to the separate segment. And the one thing that links the two segments is this point in the middle here, in which you say this point is the final point of the first segment and the beginning point of the next segment. So for this point, I can say that the final velocity of the first segment is equal to the initial velocity of the next segment. And we'll see that when we're solving problems, is that this something that comes into play sometimes. But other than that, this is all you need to know to be able to solve any problem that has to do with uniform accelerated motion. You have to identify these 5 variables, and you have to identify which equation is really going to be helpful to you to find the other variable that you're missing. Okay, so I'm going fast through this because this is recorded, so you can always go back and pause and go back, rewind, and watch another part and so on. But this is really all you need to know to be able to solve uniformly accelerated motion problems. Now let's try to solve a couple here. Let me find a couple of problems that we can put together and see how we can solve with this. And maybe I'll just pause the recording for a second in case anybody has any questions here, and then we can discuss those, and then we'll come back and solve some problems together. So here's the first example that we can go through to try to see how we can solve problems in which you have uniform accelerated motion. So suppose that you have freight trains can produce only relatively small accelerations and decelerations, where deceleration is an acceleration in the opposite direction of the velocity. And the question is, what is the final velocity of a freight train that accelerates at a rate that is given for a certain amount of time, starting with an initial velocity that is given? Okay, so we'll do A first, and then we'll see what B and C are about. So in the story for A, and by the way, this is one of the first things that I like to do when I'm thinking about these uniform accelerated motion, is I really like to draw it. I like to draw the problem, because on the problem, if I label what the things are, what the variables are, then it becomes easier to follow which equations to use. So I have a train, and that train, I want to know the final velocity of a train. Okay, so that means it's moving from one spot to another. And this is the initial story. And it gets to the final point. And it accelerates at a rate for 8 minutes. So it's accelerating. That means the acceleration is in the same direction of motion. So it was initially moving like that, and then finally it's moving like this, and accelerates with a rate that is positive. Means it's in the same direction of motion in this case. And then 8 minutes is the time interval from the beginning to the end. So I know the time interval from here to here. I don't know the distance, and I don't want you to confuse the fact that I'm labeling it like this as a distance, but this is the time interval. So I'm also wanting to find the final velocity. So that means I want to find the velocity at this point if I start with an initial velocity of 4 meters per second. So I'm given this one. So now the problem is right in front of me. The 5 kinematic variables that we've talked about before, 1, 2, 3, 4, 5, initial and final velocities, displacement, acceleration, and time. I can see them right in front of me. I can see the initial velocity here of this particular segment. I can see the final velocity. I can see the acceleration. the displacement and the time are things that are in between the initial and the final, right?
Yes.
So, if what I do in these problems is I think about the segment of motion that I'm trying to study. In this case, it's just a one segment, so it might look like it's trivial, but in general, this is what I like to do. I like to say, okay, what segment am I studying? So for part A, I'm studying the segment from this point to this point. I'm going to call them A and B. So I'm studying from A to B. That's the segment. And I like to list the 5 kinematic variables and what their values are. So I say, what is my displacement? What is my initial velocity? What is my final velocity, the acceleration, and the time interval? And I see which ones I have and which ones I'm looking for. So for the displacement, for example, in this particular case, I don't know what the displacement is. I'm not given what the displacement is. So I really don't know this one. And frankly, it doesn't really look like I care about it. I'm not being asked about it. There's nothing about it that I really care about. So I'm just going to cross it out, or maybe just leave it empty. The initial velocity, now the segment that I'm studying is from A to B. So my eye right away, when I think initial velocity, goes to right to the beginning of the segment here. It says my beginning of the segment is point A. So what is the velocity there? It's 4 meters per second. Now velocity is a vector quantity, meaning that the direction is important. So I'm going to remind myself by putting an arrow here that says anything that is pointing towards the right, I'm going to call positive. Anything that is pointing towards the left, I'm going to call negative. So since this initial velocity is pointing towards the right like that, I'm going to call it positive 4 meters per second. The final velocity, right away, my eye goes to here. That's the end of the segment. That's point B. I want to know what the velocity at this particular point is of this object, and I don't have it. In fact, this is exactly what I'm being asked for. What is the final velocity? See, that's why the question mark reminds me. What is the final velocity of the train? So this is what I'm looking for. So I put a question mark here. And then the acceleration, now the acceleration is in the same direction as what I'm calling positive. So this is a positive acceleration. And the rate that I'm given is this rate here, 0.0500 meters per second squared. So the acceleration is 0.05 meters per second squared. And it's positive because it's pointing in the same direction that I'm calling positive here. And then the time interval between the beginning and the end of the segment is 8 minutes.
Yes.
So that's something I know, so I'm just going to write 8 minutes here. And 8 minutes for me, is the time interval, but as you can see, everything is in SI units here. Everything is in meters and seconds and so on. So I'm just going to convert this to seconds because I know I need to. So I might as well just do it now. If I want to convert from meters to second, then I say here's meter and here's second. Sorry, here's minute, so I can cancel it, and here's second. So this is the conversion factor that I'm looking for. I know that 1 minute has 60 seconds in it. So that means that 8 minutes then would be 480 seconds. Yeah, good. So this is really the setup for the problems in which I think about all of the kinematic variables that are associated with this particular segment. Now, the question is asking what is the final velocity. So I'm going to try to look at the equations here, and I'm going to try to remember which things I have and which things I don't have. I have the initial velocity, the acceleration, and the time, and I'm looking for the final velocity, and I don't really care about the displacement in this case. So since I don't care about the displacement, I want an equation that doesn't have the displacement in it because I don't have it and I'm not looking for it. So I'd rather it not be part of the problem. And since we've labeled which variables are missing from the equations, then you find that this is the equation that you would use because it has the things that you're looking for, the initial velocity, it has the things that you have, the initial velocity, the acceleration, and the time, and it doesn't have the thing that you're looking for, and it has the thing that you're looking for, which is the final velocity. It doesn't have the displacement in it. It doesn't appear anywhere in this equation, but that's good because I don't have the displacement and I don't want the displacement. So this would be the equation that I would use. So I would use the equation that says final velocity is equal to initial velocity plus acceleration times time. The initial velocity is the 4 meters per second. The acceleration we've calculated, we're given the acceleration at 0.05 meters per second squared. The time we've calculated to be 480 seconds. So we can just calculate how big that is. So 0.05, that means divide by 20. So that's the zero is gone, and then this gives me 24. So this becomes 28 meters per second. Okay. So this is really sort of the layout of how I would solve a constant acceleration problem. First of all, I think about the segment, and to think about the segment, it'd be useful to draw the problem. Think about the segment, list the kinematic variables for that particular segment. What do I know? What am I missing? And then pick the particular equation from the kinematic equations that will give me the thing that I'm looking for, given the things that I have. Let's see how we can do part B, for example. Okay, it says, if the train then can slow down at a rate of this much, how long will it take to come to a stop from this velocity? This velocity then is the velocity that we were asking about in part A. So suppose that the train is already moving at that same velocity here, which is 28 meters per second. And if the train can slow down at a particular rate, slow down meaning that the acceleration is in the opposite direction of the velocity, see? That's what slowing down means. It means that the change in the velocity is negative because the velocity is going down. So the acceleration is in the opposite direction of the velocity. That's what slowing down means. At this particular rate, and notice that the rate is given for meters per second squared, so that's definitely acceleration. So the acceleration is 0.55 meters per second squared, but definitely in the opposite direction of the velocity because it's slowing down. And the question is, how long will it take to come to a stop from this velocity? Now, how long is a question about time, right? So that means I'm trying to find the time from this point to the point at which the train stops. And the question that I'm asking is, what is the time interval? Okay. So again, in this case, just like I've done before, you draw the problem and then you list the segment that you're thinking about. So suppose I call this point B, like we called it before. Right? I could have called it A and B again and studied that segment, but suppose I call it B and I call this C, just to make it a little different than part A. So then for part B, then I'd say I'm studying the segment from B to C. So now I'm thinking about a whole set of new variables: the displacement, the initial velocity, the final velocity, the acceleration, and the time of the new segment. So the initial velocity is no longer the velocity here at the beginning of the whole story. No, it's at the beginning of the segment that I'm studying. That's what it means to study a different segment. So for the displacement, that means the displacement from point B to point C. I don't know how big that is. I wasn't giving any information about how far it stops or anything like that. So I still don't know the displacement for this segment. The initial velocity now is the velocity at the beginning of the segment that I'm studying. So at point B, so that would be 28 meters per second. The final velocity would be the velocity at the end of the segment that I'm studying. So that would be point C. At point C, the velocity, it stops, right? Because I want to know how long it takes for it to stop. So that means at the end of the segment, it stops. So that means the final velocity in this case is 0. What is the acceleration during that segment? It's 0.55 meters per second squared, but it's pointing in the direction opposite the direction that I'm calling positive for all things. So because it's pointing towards the left and positive is towards the right, then I have to give this a negative sign. Right? And that really is the mathematical way of indicating that this thing is slowing down as opposed to speeding up, which is what was happening in the first problem. In this case, the acceleration is in the opposite direction of what I'm calling positive. So I'm going to give it a negative sign. And the time is the thing that I'm looking for. I'm looking for how long does it take for this thing to stop. So I'm trying to find the time in this case. Again, this is an equation. This is a story in which I don't know the displacement and I don't have the displacement. I'm not looking for the displacement. So the displacement is not a big part of what I'm doing here. What is part of what I'm doing is the initial final velocities, the acceleration and the time. So I'll find the equation that has the initial and the final velocity and the acceleration and the time. And this happens to be the same equation that we used in part A. but that's just a coincidence. So I say I have all of these four variables and I'm looking for the time. So this is the equation that I'm going to be using. But in this case, what I'm looking for is the time. I'm not looking for the final velocity. So I'm going to algebraically manipulate this equation such that I get the time from it. And that way, subtract V naught from both sides and then divide by the acceleration. So first I subtract V naught from both sides. So I get on the left-hand side, V final minus V initial, and then that's equal to AT. And then I want to isolate the time. So I'm going to divide both sides by the acceleration. So I get V final minus V initial divided by the acceleration is equal to the time. So that's really what I'm going to use because I'm looking for the time here and I isolated it. So the time then would be equal to the final minus the initial velocity is divided by the acceleration. The final velocity is the velocity 0 from here. And then the initial velocity is the velocity 28 meters per second positive. The negative just comes from the equation. And the acceleration is a negative acceleration at negative 0.55 meters per second squared. So from that, I can figure out what the time is. And I can figure out that time in seconds. And if I want to, take that and convert it to minutes or hours or whatever, I can do that. Of course, the negative signs cancel because I get negative divided by negative. And 28 divided by roughly a half will give me something like 56, maybe a little bit less than that. So maybe something like 54 or so. So it'd be like 54 seconds or something like that. Is that what I get? Maybe even less than that. Like
it's a 51, correct.
51, yeah.
Yeah.
Okay, 51 seconds. Okay. So this is how you solve kinematic problems or problems motion with constant acceleration. Part C says how far will it travel in each case? So that means in part C, we're actually looking for the displacement. So these things that we ignored in parts A and B, we're looking for that now. How far is a question of distance or displacement in this case, right? So how far means that it's asking about these delta x's here. So we can solve for that by finding any equation really that has delta x in it, because now I have the other four variables. So I can use any equation here that has delta x in it. All right. So we can do that if you want. So we can say C, oops. So for C, suppose I'm still studying the segment from A to B, and now I want to find delta x. But now I have everything else. I have the initial and the final velocity. The initial velocity is given. The final velocity is something that we found. The acceleration is given. The time is given. So really, honestly, any equation that has delta x in it would work. Let's maybe, suppose I didn't have the final velocity. So suppose I didn't calculate this, or suppose it wasn't asking the problem, or suppose that I'm not sure that I did the right thing and got the right number. So suppose I don't have the final velocity. How would I find the displacement in that case? I say, okay, let me find the equation that doesn't have the final velocity in it. That's the second one. Yeah. So I say, okay, let me take this one and use that to find the displacement. So I say, in this case, delta x is equal to V naught, the initial velocity, times the time, plus half the acceleration times the time squared. The initial velocity is given, that's 4 meters per second. Notice that the segment that I'm studying is really important because the initial velocity in this segment is 4 meters per second. The initial velocity in this segment is completely different. So it's really important for you to always remember which segment you're thinking about. In this case, I'm thinking about the first segment when the train was accelerating. So it'd be 4 meters per second times this time, not this time that I just found. It's for a different segment. This time here, which was 480 seconds, plus half the acceleration. What's the acceleration in this case? It was positive 0.05 meters per second squared times the time squared. So the 480 seconds all squared. And I can just multiply this through and figure out what the displacement is. You could do a similar thing for this part in which I'm thinking about the displacement from B to C. And again, I can use any equation because now I have everything. I have the initial velocity, the final velocity, the acceleration, and I calculated the time. So I can really use anything. But suppose I don't have the time. So suppose in this particular one, I say to myself, I don't know the time, maybe I made a mistake here. So I don't want to use this value here. So suppose I don't have the time, which equation can I use to find the displacement?
The last one?
The last one, because it's missing the time, right? It doesn't have the time in it. So I say, suppose I use the
Yes.
last one to find the displacement.
Mhm.
So I say I use this equation here, find the displacement, but I need to rearrange it to find what the displacement is in terms of the other things. So rearranging that equation, first of all, subtract V naught squared from both sides. And then to isolate the displacement, divide by twice the acceleration. So now I've isolated the displacement. Let me plug in all the numbers that I know. V squared minus V naught squared over twice the acceleration. The final velocity for this particular segment was 0,
Yes.
right? Because I'm studying from B to C. So it's important that you always remember which segment you're studying. V naught squared, that's the initial velocity of this segment. That was 28 meters per second. So this is 28 meters per second, and I have to square that. And then that's divided by twice the acceleration. If you remember, the acceleration in this case was negative 0.55 meters per second squared. Then you plug all of that, you find what the displacement is. And that gives you the answer to part C. So in this particular story, we had two segments of motion. We had the train accelerating for a bit and then decelerating for a bit. And we found the final velocity here, and that became our initial velocity in the next segment because it's the same point. And then we found in this case, we found what the final velocity is and what the displacement was. And in this case, we found the time and we found the displacement. Okay, let's do another problem that's similar to this one. So typically I would give you a chance to like do it yourself and then we can discuss it. You want to do that? You want to try a problem on your own and then we can go through it together?
Yeah, that would be great.
Okay, let's do that. So I'm gonna pause the recording so that we can discuss things, about the problem. And then if you're watching this on video, here's the problem. I'm gonna give you what the problem is. Pause the video and try to do it yourself, and then see if you can follow with us the answer that we're gonna put. Okay, here's a problem. Okay, and maybe I'll just pause the recording and then we'll come back when we're ready to start the solution to the problem. So since this problem has the acceleration is changing, we're gonna have to think about the segments separately. So first of all, I'm gonna draw the problem to recognize this. So I say the car starts out, it accelerates for part of the motion, and then at this particular point, the driver presses the brakes. So you say that means it's going to slow down, and slowing down means that the acceleration is in the opposite direction of motion, and then eventually it's going to stop. I'm working, hang on. So now that I recognize that the acceleration is going to be different, then that means I can't study the whole thing as just one segment of motion with uniform acceleration because the acceleration is changing. So I'm going to break it down again into multiple pieces. It's not going to happen in every problem, but you'll find that this is a common thing where sometimes the acceleration changes. So I have to break it down into multiple segments. So I'm going to label them. So point A is where it starts from rest, right?
Mhm.
So suppose that the vehicle accelerates from rest. So this here is at rest. And then point B is where the driver presses the brakes. And then point C is where the car stops. And then part A is what is the minimum length required for the track. So that means I'm asking about the length of the whole thing. That's the length of the track. But since the problem has multiple segments in which the acceleration changes, so that means I have to break it down into two pieces. This piece here is constant acceleration. This piece is constant acceleration. So I can study two segments here. From A to B, find what the displacement is. From B to C, find what the displacement is. And then the length of the track would be the sum of the two. So that's what we're about. So let's write down, just like we did for the train problem and for all kinematic problems, let's think about each segment on its own and write down the kinematic variables that we know. So for the segment from A to B, I'm going to be thinking about displacement, initial velocity, final velocity, acceleration, and time. From segment B to C, again, I'm going to be thinking about the same variables, but for different segment. Displacement, initial velocity, final velocity, acceleration, and time. And then what I'm looking for is I'm looking for that displacement from A to B. So that's, maybe we can call it 1 to recognize that it's this one. And we call this one 2 to recognize that it's this one. And then once we find the two displacements, we add them together, we find the length of the track. So let's do one segment at a time. We solve one segment at a time. For this segment, obviously, I'm looking for the displacement. I don't know how big it is. Let's see what else I know. The initial velocity, that means the velocity at the beginning of the segment. So that's at point A. Do I know the velocity at point A?
Yeah, 0.
Yeah, 0. Very nice, because it's at rest. So the velocity would be 0. Very nice. And then the velocity, the final velocity of the segment, that means the velocity at the end of the segment. That means at point B. Do I know the velocity at point B?
Yes, it's 40.
40 meters per second, because
Yes.
the question says once it reaches 40 meters per second, so that means at this point, the driver presses the brakes. So it's moving with 40 meters per second at this point. So this would be 40 meters per second. Let me just close this up. Okay. Where did it go? Okay, let me pause this again because I think I lost my file. So my final velocity for this segment is the velocity at point B, so that's 40 meters per second. The acceleration for this segment, well, that's a question. An engineer wants to build a track to test the acceleration from rest to 40 meters per second. Suppose that the vehicle accelerates from rest to 40 in this amount of time. I don't know the acceleration then for this segment. I just know the time. I don't know the acceleration. I just know the time for this segment. So the acceleration I don't know, and the time is 5.2 seconds. But that's okay. Since I know three variables, I know that that's enough to solve this segment. Because if you recall these four equations, the kinematic equations, each one of them has four variables in it. So that means that if you know three, you can find the fourth. So it's always critical to check for every segment here. Out of the five, you should know three of them. If you know three, you can find the other two using these equations. Okay, so let's see. This is the segment A to B. So let's solve for delta x here to find for the segment, and then we can plug in the rest for this segment. Or you know what, we might as well just put in the numbers here since we've written it down. Let's find out what these things are. Let's parse them from the diagram. So the displacement from B to C, that's the something that I'm looking for too, because I need to find the length of the whole track. The initial velocity of this segment, that means it's the velocity at the beginning of the segment. That means at point B. So for that, the velocity would be 40 meters per second. Point C is at the end of the segment. And for that, the final velocity of the segment would be at point C. And that's where it stops. So the velocity in this case would be exactly 0 because it stops. And the acceleration, I don't know what the acceleration is unless it's telling me. It is telling me. The driver presses the brakes, decelerating at this much to complete stop. So that means that I know that the acceleration is 16 meters per second squared in this direction, but this direction is opposite to everything that I've been calling positive so far. The 40 meters per second I've called positive, so that means I've picked to the right to be positive. So it means the acceleration, because it's opposite to that, would be negative. So my acceleration then would be negative 16 meters per second squared. And the negative here is indicating the direction. It's indicating that the change in velocity is in the opposite direction of the actual velocity.
Dr. Musa,
Yes, Tasneem.
so is it correct to always think that whenever something is slowing down, it will be negative?
So here's one way that that would not be the case. Suppose that I have, somebody threw a ball this way, right? And I've decided that this is my positive. Now, if it's moving, let's say at 20 meters per second in this direction, and then it goes down to like 5 meters per second like this, that means the acceleration is in this direction. In this case, the velocities are negative and the acceleration is positive. So I suppose what I'm trying to say is that positive and the negative story is an interpretation of the direction information that is up to you what your choice of the coordinate system is. Because the coordinate system is something, it's a tool that you use. So then you say, you decide which direction is positive. For example, in this problem that we're solving right now with these cars, I could say that to the left is positive. It's up to me. So that means I can say, I can call the 40 meters per second negative, but then the acceleration would be positive because it's in the same direction that I'm choosing. Okay, so it's a choice, but you have to be consistent with it. Once I choose one direction to be positive, I have to be consistent. Every variable that is in that direction would be positive, and every variable that is in the opposite direction of that would be negative. Good question, Tasneem. Thanks for asking.
Yeah, I remember I saw something in regards like the video of velocity and speed that they said the same thing. It's up to you, but it still confuses me sometimes. So that's why I wanted to ask. But
Yeah, so maybe you fix it for yourself then. Say to the right is positive and and fix it from then on. So every time in your mind when you're solving a problem, you say to the right is positive, so that means everything that is pointing to the right I'm going to call positive, and everything that is pointing towards the left I'm going to call negative. And fix that for yourself once and for all. That's a good thing. The thing is, in some other problems that we'll solve, you'll find, for example, that up and down is also some problems we can solve, when you throw something upwards and so on. So you might call up positive and down negative in that case. So maybe you always think, if it's to the right or up, I'm going to call these positive. If it's to the left or down, I'm going to call these negative. Yeah. And in some other problems too that you might see, you might have something that is sliding on a slope like that. So this would be the direction of motion like this. So you say, okay, you know what, maybe I'll pick this direction to be positive. So the velocity in this case would be positive because it's pointing like that. Maybe it's slowing down because, friction is stopping it or something like that. So it's slowing down. So the acceleration is in the opposite direction. So it'll be negative and so on. Okay. So for each problem, I guess to answer the question in a general way is that for each problem, you decide which direction is going to be positive, and all of the vectors pointing in that direction would be positive for you, and all of the direction pointing opposite would be negative. Good question. Okay, back to our problem. For B to C, I don't know what the time is, so frankly, my dear, I don't really care about this. So, but it's enough that I have three variables, right? I know that if I have three variables, I'm happy, so I can solve that. Okay, so let's solve A to B to find delta x1. Let's solve B to C, find delta x2, and then we'll add them together to find the length of the track. So from A to B, I know that I have the initial velocity, the final velocity, and the time. So let's see if there's an equation that can help me find the displacement from that. Maybe I'll just grab these equations here and I'm going to put them next to me so that I don't keep scrolling up and down. I'll put them next to me here. So I want to think about which equation has the things that I know and the things that I'm looking for. So this one has initial velocity, final velocity, and time.
Yeah.
And I'm looking for the displacement. So it's that first equation, right?
Yes, first one.
because I have initial velocity, I have final velocity, and I have time, and I'm looking for displacement. So this
Mhm.
works. So then I say use delta x is equal to half v naught plus v final times the time. And I honestly don't even need to switch it around because that's exactly what I'm looking for, the delta x. So I can just plug in. The initial velocity is 0. The final velocity is 40 meters per second. And the time I'm given is 5.2 seconds. So I can just say that this is 2.6, 2.5 will give me 100, and the 0.1 will give me 4. So this is 104 meters. Okay, so this part here is 104 meters. Now I need to find this part, and for this part I need to think about b to c, and we already laid out the variables, and I just need to find delta x2. Now I need to look for an equation that has the displacement, the initial and final velocities, and the acceleration. It doesn't have the time because I don't know the time.
And the last one.
The last one, very nice, because it has the displacement, which is I'm looking for, the final and the initial velocities, and the acceleration. So I can use that one, but I need to rearrange it to find delta x.
Mhm.
So from b to c, I'm going to use that v final squared is equal to v initial squared plus twice the acceleration times the displacement. But I'm going to rearrange it to find the displacement. And the way to do that is subtract v naught squared from both sides, and then divide both sides by the acceleration. So you get that v final squared minus v initial squared divided by twice the acceleration is equal to the displacement. So that means then the displacement is equal to this stuff here. Final velocity is 0. The initial velocity is 40. And when I square that, square 40 becomes 1600. And then divided by twice the acceleration. So 1600 divided by 16 gives me 100, divided by 2 gives me 50.
50. Yeah.
Very nice. So this is 104 meters and this is 50 meters. So together, the
54.
displacement, very nice. So for A to C, the whole length of the track is the sum of the two. Okay. Does anybody have any questions? Is that clear?